remember our process is to find the first derivatives, and you find where they are zero. The values at which both are zero are called critical points. Once you find the critical points, you then compute something called D. And if D is positive, then you might have a max, or you might have a min. You determine whether it's a max or a min by looking at the second derivative. So if the second derivative is negative, then your concavity is downward and you have a max. If your second derivative is positive, then your concavity is upward and you have a min. Notice I put XX here and I put YY here because once you know D is positive, they both have to be the same sign. F double X and F double Y both have to be the same sign in order for D to be positive. So it doesn't matter which one you check. If you feel like checking both, you can. If D is negative, then we have a saddle point. And if D is zero or somehow undefined, then you have to do more work. Like it's inconclusive and you have to rely on other. Okay, so for this example, my derivative with respect to x will be 1/2 x plus 4 squared plus y minus 5 squared to be minus 1/2. I'm taking the derivative with respect to x, and so the chain rule would have me multiply by 2 times x plus 4 to the first power. Because this has no x's in it, its derivative is 0, and the 8, its derivative will be 0. So cleaning this up a little bit, I get x plus 4 over the square root of. Okay, z sub y will basically be the same, except now this term's derivative will be 0, and the chain rule will tell us to multiply by 2 times y minus 5 to the first power. Okay, so there are my 2 first derivatives. And we are interested when they are 0 or undefined. It's just if they're we should probably also look at where they are undefined, but fractions only can be 0 if the numerator is 0. So if I were looking for where this would equal 0, it would equal 0 at x plus 4 equaling 0, so x would be negative 4. This ratio would be 0 where y minus 5 would be 0, and so y would equal 5. But if you notice, if I plug negative 4 and 5 into the denominator of my derivatives, they equal 0. So technically, the critical point is x equals negative 4, y equals 5, but it makes my first derivatives undefined. Because my first derivatives are undefined at that point, the second derivatives will also be undefined at that point. And so there's not a reason to find D or to find our second derivatives, because they will be undefined at our point, because the derivatives are undefined at that point. But when you have derivatives that are undefined, but the function itself is defined, so notice if you plug -4 and 5 into the original function, z of -4, 5 gives me 8, so the function itself is defined at that point, but my derivatives are undefined. When you have that situation, you either have, I mean, you could have some gap in the graph because the function could be defined at a point and then there's a jump, but often with surfaces, it means that you've got a sharp point in some way, that coming in from one direction, the slopes create a sharp point compared to how you're coming in from another direction. And that's what you could see here from our graph. So the extreme point, we do have a minimum. If you did not have the graph in front of you, so if you didn't have the 3D graph to test what is going on at that point, you could, some things that you could do. One, if I square both sides, I get, well, actually, you know what I think I'll do? I'll subtract 8, and then I'll square both sides. And if you go back to chapter 12.6, this form is fitting the form for a cone. One thing to, so I'm reviewing the discussion from section 12.6 right now. If I plug 5 in for y, okay, so if I plug 5 in for y, this becomes 0, and I'm left with this equation here. Notice if I take the square root now of this equation, so if y equals 5, then you would end up with, and if I took the square root of this equation, notice I get a line in the xz plane. If x equaled -4, then I would obtain this equation, which is equivalent to this line in the zy plane if you take the square root of both sides. So if you go back to section 12.6, and we were studying all those different quartic surfaces, one way to recognize the cones, I mean, there was a couple of things that if you were trying to look at quick patterns to recognize, do I have an ellipsoid, do I have a paraboloid, do I have a cone, do I have a hyperboloid? The cones, all 3 variables are squared, but one has a different sign. Okay, all 3 are squared, but one has a different sign. So notice z is on the other side of the equal sign, so if I put it on the other side, it would have a negative sign. And then another way to recognize the cones are to do what I was just pointing out here. Zero out one of the variables, and then you'll see you end up with a line, and so that's what's creating your cone shape. The fact that you can simplify it. When you zero out one of the variables, you get a linear slice. That indicates that you have a cone. So again, if we did not have our Mathematica graph of this function, you could do what I just did over there and realize, oh, you know what, I have a cone, so this point where my derivative is undefined should be a sharp point. it could be a minimum or it could be a maximum depending on whether I had this part of the cone or whether I have that part of the cone. But a way to tell that is, notice everything, the way this is written, everything's positive, so I must have this part of the cone and not that part of the cone. And so it should be a minimum point. You also could plug a point in that's kind of close to this. So, for example, I could plug in negative 4.1, 5.2. Okay, plug in a point that's kind of close to that, and you should get a value that's higher than 8 when you do that. So, so again, when you don't necessarily have a graph in front of you, you know, these are just little tricks that people do. One, if it happens to be a common shape, you could work off of knowledge of what the shape is. Two, you could plug in points that are close to it and see what is happening. Okay, so when I plug this point in, Z is equal to 8.22, so it's higher than 8. When I plug negative 4.5 in, I got 8. So again, that's indicating that this must be a minimum point, not a maximum point, because when I plug points in near it, I get values that are higher. So since 8.22 is greater than 8, the point negative 458 must be a minimum. Okay, so here was an example where we couldn't, our typical system of find the critical points, find D, see if it's positive, see if it's negative. Instead, we ended up with this situation where D is undefined because my second derivatives are undefined, because my first derivatives were undefined, and so I had to do other investigation. In this case, the other investigation included recognizing that it's a cone from section 12.6, recognizing that it must be the minimum because I have the upper side of the cone because it's positive, but then also if you plug in a point nearby your critical point, I get a value that's higher than when I plug in the critical point, hence I must have hit a minimum. Alright, so the set of examples that I gave you kind of runs the gamut of different things that can come up. I know some of them, the algebra work was real messy, others, they were not so messy. But I figure if we hit the really messy ones in class, then the stuff that shows up on your homework won't seem as bad. And then the last class I pointed out that little strategy of taking expressions that get used over and over again in a calculation, like make a little symbol for that that's easier to write, and then you don't necessarily have to write as much stuff down. And you know, Issa, I'll have to dig it out, but just because I basically felt like you were trying